right, welcome to Unit 6, Chemical Equilibrium, something we've been looking forward to all year, and now we're finally here. So let's just dive right into it. This is the introduction to Unit 6. Again, discussing chemical equilibrium. This is a fairly long unit, and that's okay, but it's also probably the most tested unit on the AP exam. So we know that when a chemical reaction happens, that typically when that reaction happens, you have, for example, methane gas reacts with oxygen to make carbon dioxide and water. And when that happens, it's very, very unlikely that carbon dioxide and water would react to go backwards to reform the methane gas and the oxygen gas. So this reaction here, the methane reaction, is a reaction that goes in one direction, and really one direction only. It goes to the right, forming carbon dioxide and water. However, there are a lot of reactions where as the products begin to form, the products will actually react with themselves to reform the reactants. For example, in the case of a weak acid such as HF, when you put hydrogen fluoride into water, what it does is it does to a very small extent dissociate into H plus and F minus. But as the hydrogen ions and the fluoride ions begin to form, they also will react with each other and go in the backward direction to reform the HF molecule. And what that does, when you have this situation right here, where as the reactants react to form products, and then the products react to reform the reactants, you get a system of what's called equilibrium. Okay, and what that means is it means that that reaction is reversible. It goes in one direction, but it also goes in the reverse direction as well. Okay, this happens a lot in biology. It also happens a lot in the environment. Again, as water evaporates and condenses in the atmosphere, there's carbon in the carbon cycle. There's oxygen in our hemoglobin inside of our bodies. It does happen a lot in our real life. Okay, in terms of the chemistry that you'll encounter in the AP course, such examples include a solid dissolving and then crystallizing again. So the solid will dissolve, and that is it turning into an aqueous solution, and then you get rid of the water by boiling it off, and it crystallizes. You can have electrons being lost and gained in what are called oxidation reduction reactions, which we'll cover in Unit 7. And then obviously hydrogen ions being exchanged in acid-base reactions, which we're going to get into much more detail here in this unit. Okay, many of these processes and reactions will be accompanied by some type of something you can observe. You might see a color change happen. You might feel some heat. You might see a gas being released, etc. Okay, and again, when we talk about equilibrium, we refer to it as a dynamic equilibrium. And dynamic just means that to our eyes, it looks like the reaction has stopped. However, what really occurs is that the reaction has started going, as it's going forward, it also starts going backwards. And when the rate, so remember, think of kinetics, when the rate of the forward reaction is equal to the rate of the backward reaction, we are now at what we call equilibrium. And for a reaction to reach equilibrium, obviously you need some time to pass. The reactants have to be allowed to form products, and then the products have to be able to start the reverse reaction, etc. The nice about equilibrium is it doesn't talk anything about speed. Okay, remember, speed is all about kinetics in Unit 4. Equilibrium has nothing to do with kinetics or speed at all. Okay, so we know that at the beginning of a reaction, the reactant concentrations are usually very high. A lot of times there's no product at all when you start a reaction. Most of the times there's no product at all. Sometimes with equilibrium you can, but in general, at the beginning, the reactant concentrations are high, and so the rate is also high. Again, we've learned that in Unit 4. At this point, the product concentrations are low, and again, usually 0. And there is no backward reaction at all, and if there is, it's very, very low. Okay, as the reaction starts to go, though, the reactant concentration will start to go down since we're using up the reactants, and then the rate of at the same time, the rate of the forward reaction will also start to go down. And as those product concentrations increase, so as we start to make products, the backward reaction will start to go faster. So as the product concentrations increase, the rate of the backward reaction is going to increase. And then again, that point at which the rate of the forward reaction and the backward reaction are the same is when equilibrium has been established. So equilibrium is established when the rate of the forward reaction and the rate of the backward reaction are the same. And again, it takes some time for it to get there. Okay, at this point, since reactants and products are being converted to each other at the same rate, their concentrations don't change, and basically, from our point of view, it looks like the reaction has stopped. So the blue one here, this is the reactants. The red one here, that is the products. So you can see at the beginning here, this is concentration. At the beginning, the concentration of the reactants goes down, but then right about here, you get to a point where now the concentration of the reactants remains the same, and then same thing with the products. As its concentration goes up, it gets to a point where the concentrations remain the same, and therefore at this point right here in our experiment, we have now reached equilibrium. Okay, once equilibrium has been established, a sudden introduction of reactants. Okay, so if all of a sudden you added a bunch of reactants, this would result in a sudden dramatic increase of the forward reaction rate. So if all of a sudden you added some more whatever, if you added some more, let's say some HF to this equilibrium system right here, well, what happened is all of a sudden there would be a dramatic increase of the forward reaction rate. But then again, after the spike in the forward rate, a new constant forward reaction rate would be established, and the same thing could be applied to the reverse reaction. If you added a bunch of products, all of a sudden the reaction, you'd see that sudden dramatic increase in the reverse reaction, causing the reaction to speed up going in the reverse direction. Okay, and again, when equilibrium has been achieved on a macroscopic scale, so from our point of view, to us, it looks like, well, nothing's happening. The reaction has stopped. Okay, but that is not the case at all. They're just going at the same rate. So when equilibrium has been established, there are both products and reactants present in the reaction mixture. If those products and reactants have observable differences, for example, they have different colors, the reaction mixture will often appear as a combination of the two. For example, the mixture below will often appear purple in color because you've got an equilibrium system that has this red component in it and then also has this blue component in it. So when the reaction's at equilibrium, you're going to see a combination of the two producing a purplish color. Okay, and then depending on if it's a little bit more red or a little bit more blue, you could predict and say, oh, there must be more reactant or there must be more product, depending on if it looks more reddish or bluish. All right, so let's get to the heart of this component here dealing with equilibrium, is what's called the equilibrium constant. Okay, the equilibrium constant, the general form of the equilibrium constant is written as KEQ. And EQ stands for equilibrium. And K obviously stands for the constant. Now, it's not like the gas constant in that it's always, R is always 0.08206. Okay, this is an equilibrium constant that unfortunately changes quite often. So it's not a fixed number. It does tell you some things that we're going to talk about here in just a minute. But KEQ is basically the general form of that equilibrium equation. And the way that you determine the equilibrium constant is what we see here. We have a balanced equation. Now, in that balanced equation, the capital letters would be like H2O, CO2, etc. Whereas the lowercase letters would be the coefficients in the balanced equation. So let's go back real quickly. Let's go back to Unit 4 when we talked about rate laws. If you had this equation right here and you had to write the rate law, the rate would equal K times the concentration of A raised to some power. And again, we would have to look at experimental data to determine that. and then it would be times B, also raised to some power that we would have to figure out. When dealing with rate laws, you only include the reactants. Okay. However, with equilibrium constants, as you can see, the expression for the equilibrium constant is the concentration of the products on the top. I can't stress that enough, that the concentration of the products go on top and the concentration of the reactants is on the bottom. And you'll notice that instead of KEQ, I wrote KC here. And what that C stands for is it means that it's in terms of concentration. So that lowercase c in KC means it's the equilibrium constant in terms of the concentration. And again, notice how I write the concentration. When you write square bracket C, that means the concentration of C, and it's in terms of molarity. Okay, so those square brackets, and that's really important that you include those. If you don't include those, it's incorrect. Okay, so you'll notice that it is the concentration of the product, C and D, raised to the power of its coefficients. Okay, this is like the basic, this is kind of like the, hi, welcome to the problem. Here's a real easy one to get you started. Many times they'll make you write, this is called the equilibrium constant expression. Many times they will make you write an equilibrium constant expression when you, at the beginning of a problem dealing with equilibrium. Okay, so it is the concentration of the products raised to the power of their coefficients over the concentration of the reactants, again, raised to their coefficients. So in this case, there's no like rate laws where you have to look at data to determine the powers. First of all, these aren't powers, or they aren't orders. Whatever the coefficient is, that's the number that goes up into the corner. Okay, so the square brackets represents equilibrium concentrations. So it's the product of the equilibrium concentration of the products raised to their stoichiometric powers, to the coefficient from the balanced equation, divided by the product of the equilibrium concentrations of the reactants raised to their stoichiometry power. And here's a great piece right here, is that the equilibrium constant has no units. Now, what that means is it means that when you get done, you just write a number, and that's all you write. Do not ever add anything after an equilibrium constant once you're calculating that value. Okay, now another thing we need to think about is, okay, well, when we talk about concentrations, concentration deals with the moles over the volume. Okay, but if you think about it, well, if you have a pure solid, let's say you have some AgNO3 solid, oh, that's not a good example because it's not a solid, but let's say you have some silver chloride, that's a solid, in a solution, and that's sitting on the bottom. And I say, what's the concentration of the silver chloride? Well, it's the moles of silver chloride dissolved in the solution, but wait, it's not dissolved in the solution. So, wait a minute, so what's the concentration? It doesn't really have a concentration associated with it. Okay, and so what that means is it means that KC expressions do not include values for pure solids or pure liquids. So what that means is in your balanced equation, let's come back up here, in your balanced equation here, if one of them is a solid or one of them is a liquid, pure solids or liquids, then you do not include it in your equilibrium constant expression. Okay? So you do not put solids or liquids into the equilibrium constant expression. So KEQ is the general way of writing the equilibrium constant expression. Okay, and then again, it's really there to help you. If they say KC, what that means is they want the equilibrium constant and they want it in terms of, like we can see here, concentrations. Okay, here's another note here. When dealing with gases, though, KC can still be used. Okay, think about the moles of a gas over the volume of a gas. Can you calculate that? Of course you can. Okay, so when you have a gas, can you still use KC with gases? Absolutely, yes, you can. Okay, you can take the moles of the gas and you can divide by the volume of the gas and get the concentration. Okay, however, another form of the equilibrium constant expression is called Kp. And in this case, the P stands for pressure. Okay, and so what it is, it's the same thing. It's the equilibrium constant of the products on the top, the reactants on the bottom, raised to the power of the coefficients in the balanced equation. But instead of concentration, notice the way that they write it is they put P and then of whatever that product is. So instead of, you do not use square brackets, you just use regular parentheses. And when you write it in such a way that, again, you write the pressure of something, not the concentration of something. Okay, so here's an example of this. Okay, it says the Haber process is a process by which hydrogen and nitrogen are converted into ammonia by the following equation. So notice, first of all, they're all gases. It says write the equilibrium constant expression for this reaction in terms of Kc and also in terms of Kp. So let's start with Kc just because that's the first one. So Kc is going to equal the concentration of the products. So the product is NH3. So the concentration of NH3, and there's two of them, so that's squared. So it's the concentration of NH3 squared divided by the concentration of N2, and there's only one of them, so I don't add anything to that, times the concentration of H2, and that is cubed. Okay, and that is, and when they say the equilibrium constant expression, that right there is the equilibrium constant expression. Okay, we could also do the same thing with Kp, but instead of concentration of NH3, we're going to write the pressure of NH3 squared, that's our product, over the pressure of N2 times the pressure of H2, and that is cubed. So they look exactly the same, other than if it's concentration, if it's Kc, you have to use these square brackets. And if it's Kp, you have to put the letter P in there. But then everything else, it's raised to the same power, it's still products over reactants, etc. Okay, example number 2. Dinitrogen tetroxide and nitrogen dioxide exist in a state of equilibrium expressed by the following reaction. What is the equilibrium constant expression Kc for this reaction? So Kc would equal the concentration of NO2 squared over the concentration of N2O4. Notice the square brackets. Notice it's products over reactants. Notice it is raised to the power. It doesn't ask us for this, but if they did say what's the Kp expression, then we would write the pressure of NO2 squared over the pressure of N2O4. Okay, now it's saying, okay, if the concentration of NO2 is 0.526 molar and the concentration of N2O4 is 0.0429, what is, so now they're actually saying, all right, what is this number? So now we're going to take our calculator and we're going to place those numbers into the Kc expression. So Kc is going to equal the concentration of NO2, which is 0.526, and again, just leave out the molarity part because there's no units, squared, over 0.0429, again, leave the units out, so 0.526 squared, don't forget to square it, divided by 0.0429 is equal to 6.45. Okay, and that is our equilibrium constant value based on those values right there that they've given us. Now, what does that number mean? We'll get there in just a little bit. Okay. Now, example 3. Okay, just one. Notice that on both of these, gases, all of these were gases, but here we have one where we have a solid included in there. So remember the equilibrium constant expression. Write the equilibrium constant expression for the following reaction. Now you'll notice, first of all, there's a solid, but there's also two aqueous solutions. So, well, do I have to write Kc? Could I just write K? You could. Okay, again, I would write Kc So it's the concentration of the products. So it's the concentration of Pb2 plus times the concentration of Cl minus, and that is squared. Now that would be over the reactants, but again, since PbCl2 is a solid, we are not going to include it in our equilibrium constant expression, and so therefore that is the final answer. And then just like up here, you could put that number in, you could put numbers in, and then you could solve for the equilibrium constants. Okay, last thing here real quickly. So equilibrium constants can be very small or they can be very large. Okay, what does that number actually mean? So in this, for example, what does that 6.45 mean? Well, if you think about it, it's the concentration of the products over the reactants. Okay, and in this case, if our value here is greater than 1, and you can see it here in the problem, it means that even though you're at equilibrium, remember, equilibrium doesn't mean you have the same amount of reactants and the same amount of products. It just means that the reactions are going at the same speed in opposite directions. Okay, but at equilibrium, you might have more products, you might have more reactants. Okay, and so what the equilibrium constant tells you is it basically gives you a ratio of the products on top to the reactants on the bottom. And if the number on the top is bigger, then KEQ, or the equilibrium constant, is greater than 1. So a large value for K, which basically means it's greater than 1, means that the equilibrium lies to the right, is the way that they say it. And really what that means is it means that you have mostly products in your equilibrium mixture. Look at it up here. I mean, here we have it. Even though we're at equilibrium here, look at the concentrations of NO2 versus N2O4. We've got way more NO2, the concentration is 0.526, versus N2O4, 0.0429. So all this number really tells us is that we have a lot more of our product than we do our reactant. Okay? However, if you have a small value for K, it means the reaction lies to the left. And again, what does small mean? It means less than 1. And that means you have mostly reactants. Obviously, if this number were bigger, then of course your K value, your equilibrium value, would be less than 1. If this is a bigger number and this is a smaller number, then you're going to have a value that's less than 1. But again, what does that really mean? It just means you have more reactants than you do products in your equilibrium. So if KEQ is greater than 1, the reaction lies to the right, which means, again, you have mostly products. If your equilibrium constant is less than 1, then your equilibrium lies to the left, which means you have mostly reactants. Okay, so that's all that number really tells you. Okay, now equilibrium constants, again, are not like the gas constant are. Okay, they obviously can change. Okay, they are not constant. Okay, and when certain conditions change, the equilibrium constant can change. However, if you change your initial amounts of the initial concentrations, the equilibrium constant does not change when those initial concentrations vary. Because remember, when you start with your initial concentrations, it still has to reach equilibrium. So once the reaction reaches equilibrium, those ratios, the amount of reactants to products, like here, for example, the ratio of the NO2 to the N2O4 will still be the same. It doesn't matter what you start with. So looking at that example, let's say like in experiments 1, 2, and 3, you start with no N2O4 and you start with some NO2, but you have a different amount every time. Once you reach equilibrium, these are your pressures of your products and reactants, but notice your equilibrium constant still stays almost exactly the same. And even if you start in experiment 4, if you start in experiment 4 with some N2O4 and no NO2, and if you think about it, N2O4 is the reactant, here NO2 was a product, it doesn't matter how much you start with, you'll notice that no matter what you start with, the ratio of reactants to products is always the same. So changing the initial amounts of the reactants and the products does not affect the value of the equilibrium constant. Again, some things do. Some things are going to make the equilibrium constant change, which we'll get to later on. But for right now, understand that the equilibrium constant does not depend on how much you start with. Because no matter what you start with, reactants or products, once it reaches equilibrium, the ratio of the reactants to products always remains the same.